Let's start the second lecture by Ingo. Please, Ingo, I like that.
Okay, thank you. Good. Written a little bit of a recap where we ended 2 days ago. So I tried to not define but describe a theory which is not mass, but which one would maybe expect to get out of a rational DOA, which is a 3-dimensional quantum field theory, which is topological in the interior of the 3-manifold and is holomorphic on the boundary of the 3-manifold. So what that means is, so what does it do? So here's a configuration to which this 3-dimensional theory would want to assign a number. So it's a 3-manifold. Inside the 3-manifold, there's some ribbon graph built out of the category of representations of V. Then on the boundary, there are some, so on the boundary, firstly, there's a complex structure and also an orientation. The 3-manifold is also oriented. Then on the boundary, we have marked points. So the points, so that's not entirely sort of finished. So for these points, so there's a marked point and there's a local coordinate, phi1, phi2, and so on, which maps a neighborhood of the point holomorphically to a neighborhood of 0 in the complex plane. And then also at each point, we specify a vector in the representation of the VOA, which labels the 1-dimensional line, straight line, which ends at that point. And then if we give such a decorated 3-manifold with a complex boundary, then the theory assigns to this a complex number. That's the idea. And then we said we now want to use this to separate the question of describing, so I want to later use this to describe correlators, and I want to split the problem into a problem which is a purely topological field theory problem and something which tries to relate topological field theory to conformal blocks. And the idea was to cut out a neighborhood of this boundary so that, so here's a little annulus sigma times interval. So that's what I've drawn over there. And then I can describe different manifolds by gluing in different 3-dimensional parts here. And so this is all topological now. The only complex structure happens on the boundary here. So if you do this, you're led to a picture like this one, where I've got a surface sigma with complex structure. The underline means that I want to not have only the surface, but it also comes with this decoration of marked points and local coordinates and maybe a representation labeling it. And so this boundary does have a complex structure or conformal structure, but it's not parametrized. It's a free boundary. It's not a gluing boundary as in a TFT. It's a free boundary. It's not parametrized. So I take this surface. I forget the complex structure. I take it times an interval. That's my 3-manifold. And then the inner boundary here is of course still sigma, but now without the complex structure. But it is parametrized by itself in this case. And so this is a parametrized boundary without complex structure, it's topological. And so that's a gluing boundary for the TFT. Right? And then wherever I have a marked point, I now get a ribbon which, or a line which stretches from one boundary to the other. And so and from this point of view, what does it describe? So let me rewrite this slightly. So suppose you don't actually for each of these points also pick a vector, but you keep this choice free, well, then you don't get a number. What instead you get here is a linear functional, which goes from the tensor product of all the decorations to the complex numbers. And this linear functional would then be an element in the space of conformal blocks for the surface with its complex structure, decorated by these representations R1 to Rn. Right, and so therefore, what we expect this to describe is for each state of the TFT, I put on the interior boundary, it should describe a conformal block for the corresponding set of representations. Right, and so this is not mass, I keep saying, but bits of it are. And so let's make a little wish list of what we would want this linear map to satisfy. We first of all would like it to be an isomorphism, so that indeed all the conformal blocks are actually described by states of the TFT in here. We want it to be compatible with mapping class group representations, and we want it to be compatible with sewing. So what I want to do now is to make describe by example the last 2 points, and then sort of more formally saying what this wants to be. It is a map which relates a topological modular functor to a complex modular functor. I'll not define any of these 2 things, so but that's what it wants to be. That's, I think, basically how far we got. Are there any questions or comments? Okay, so then I wanted to do this aside. Yesterday we had a talk by Kalle, and he had the easing model on domains in the complex plane, and then he mapped that to the upper half plane and got some functions Sn, which may be dependent on some boundary condition for the easing model. And as a little teaser for what may possibly happen in the third lecture, is that this in this language, these functions Sn would be described by such a picture, I claim. That is something I try to explain in the third lecture. But so let's look at it a little bit. We have a 3-ball here. The boundary we parameterize by C with infinity, so by P1 with a specific choice of quasi-global coordinate. Then on here, we have a map which is complex conjugation. It's an anti-holomorphic involution. And so what I'm describing is the Schottky double of the upper half plane. And I want to think of this as the boundary of my 3-ball. Then inside the upper half plane, I had a number of marked points at 1 to Zn. Well, I can use this involution to reflect it to the lower half plane, and I get Z1 bar to Zn bar. And then inside my 3-ball, I connect them by ribbons labeled by the sigma representation of the C equals a half Virasoro BOA. And then I claim now to describe different boundary conditions, I should sort of have a little ribbon which is just inside the 3 manifolds parallel to the equator, which is the image of the real line, which sort of catches all these lines which go from top to bottom. Then for each of these points, of course, I've got local coordinates, which are just standard local coordinates on the plane. At each of these points, I insert the highest weight vector of the lowest weight vector of the corresponding representation. Then according to this philosophy, that should now be a number. And I'm saying that that number is this Sn, which Kalle had in his talk. And the different B's, the boundary conditions in this language, are just different representations. So different objects in the easing modular fusion category. And so if you choose B to be the tensor unit, then that would correspond, it's a choice of convention, but that would correspond to the plus boundary condition, the lattice description. If you choose it to be the object sigma, it would be the free boundary condition. If you make this B here epsilon, that would be the minus boundary condition. And to see that this at least vaguely makes sense, you can do a little topological field theory exercise and show that this is 0 if n is odd and the boundary condition is sigma. Sorry, for P is sigma. So that's on the TFT computation, and so that's exercise.
In this picture, if you change the boundary condition, like free and plus,
well, you want a bit of it to be free and a bit of it to be plus?
Yes, like to insert what we call BCC.
So there are 2 ways to do this. So let's say we want to. So none of this will make sense because I'll only explain this a little bit in the third lecture, right? So suppose we have an epsilon here, which is a minus, and the free on this stretch here. And well, so this is not a valid decoration of a ribbon graph in the 3 manifold because there's no morphism you can put from F to epsilon. So you can either decide to sort of have a line branch off in the interior and wander through here and connect to this. For example, I think you might want this to be an F line. So this describes now a easing correlator in the upper half plane with a topological defect labeled by sigma. Not mix notation too much. That's one thing you could do. Or you could say, well, I don't want this. You could have the sigma ribbon branch off and connect to the outside here. Well, now you have new points which end on the conformal boundary, right? So you get a different conformal block. And so the interpretation of this will be that it's an insertion of two boundary changing fields in the CFT. Right. But yeah, we will hopefully get to that. Come on. Are there more questions or comments? So back to this.
Who's doing the exercise?
Who?
The audience or Marco?
No, so after this lecture, you'll be like, oh, I want to do the exercises, and then you'll sit down and do the exercises, and we will be able to solve them because you all have experience. So how does this one? So here's a hint. Look up what a Hopf link is. Then remember that in the easing fusion category, the Hopf link where both of these are labeled by sigma is 0. And so stare at this for a long time, and then you can do this exercise. Good. So I wanted to now give maybe an example of what these two things mean: mapping class group compatibility and sewing. So let's do the property 2 there. So let's see. So I draw a little cartoon of the picture I had there. So out here again we have the conformal boundary. In here we have the topological boundary, and it's parameterized by the identity. And so now suppose in my moduli space of complex structures, I walk a closed path, and then if I come back to the same configuration, well, I should be able to compare this. So let's say my closed path is I take one of these insertion points around another. So I do this by wiping now, because I don't want to redraw the picture so often. Or maybe I will do it once. So let me keep this one there. So inner boundary is still parameterized by the identity. So what would that look like? Did I do that the right way around? Probably not. I did draw this here. Okay. So if I do this, if I go this path in moduli space up there, and I end up with this configuration. Well, that configuration is now different from this. So let's try to make this configuration look like our standard configuration again. Well, what I can do is I can apply a mapping class group element to the inner surface. So I can just apply a sort of 2 gain twists which undo this rotation here. So let me denote this element of the mapping class group by F. So I apply F, so then I can get back to this configuration, but I've now changed the parameterization of my boundary, right? Because that's a parameterized boundary, so it's no longer parameterized by the identity, but it's now parameterized by the mapping class group element, which undid this rotation. Right, so that's still different from this, because now the inner boundary is not parameterized by the identity, but by F. Parameterizing a boundary in this TFT language by a mapping class group element, I can always trade that for using, instead of F, I can use the mapping cylinder MF and apply the TFT to that. That would give me a something I should find this. So I want to rewrite it like this. So here I do the identity, but then I go from sigma bar to sigma bar with F. Well, that in turn I can trade for gluing in here the mapping cylinder for F. Right. So then I am in. So if I do the mapping cylinder, then indeed I'm in a situation where I've again parameterized all the boundaries by the identity. Then I've got this free manifold, which is the surface times an interval, and in the middle you cut it open and you put your mapping class group element F. Right. And so what we've done now is, so this is again my standard configuration like there, and I'm saying that if I carry out such a closed path in the modular space, which translates into a mapping class group element, then this has to, all of this these are identities, right? This has to be equal to this. And so in this sense, I want this object to intertwine the mapping class group action. So it trades this path for the corresponding mapping class, mapping cylinder acting on acting via TFT. Does that make sense?
You say the isomorphism, the top line intertwines mapping class group actions.
So my field, my three-dimensional theory, which comes out of the BA, would evaluate this three-manifold to this isomorphism. Right, and so this isomorphism is what is represented by this picture. And this isomorphism satisfies that if I apply this transformation on the complex boundary, well, that agrees with gluing in the mapping cylinder on the inner boundary. More questions or comments? Doing. Now, sewing. So we do sewing. So what's the situation there? So we have, suppose we have a complex surface. So I'm drawing a bit of it here and a bit of it here. Not care if it's sort of otherwise connected or not connected. Maybe here I've got a point U and a point V. They all come, they have some neighborhood on which I have these coordinate functions defined. And so they all go to C, they map U to 0. And then out of this, I can define a new complex surface by a new, so I get a new surface with complex structure by sewing. So let me pick a number which is a non-zero complex number, which I want to be small enough. Say what that means. And then for each such cube, I can get a new surface by identifying points here and here according to the rule. So if I've got a point Z here and a point W here, I want to identify them if phi U of Z times phi V of W is equal to Q. Right? And so that's the usual sewing formulation. And so I get a whole family of surfaces here. And okay, you can ask, why do I want this family? Can't I just take Q as 1? And indeed, you can do that. Then you have a preferred sewing, but that restricts on which points you can sew. Because then what can happen to you if you want this to be 1? It could happen that these coordinates don't extend far enough so that there are even instances of 2 points which multiply to 1. And really, you need both of them to be in here. You need both of them to be defined on an annulus. And so you can either guarantee this by saying, okay, I only can glue certain local coordinates, and you may have to adapt the local coordinates to be able to glue, or you introduce this parameter, and you don't have to put restrictions on the coordinates, but you get these families. So that's up to you. So let's do this. And so let me write this new surface. So if I glue this to this, right? So then this new surface will look a little bit like this. So here's the one patch and the other patch, and now I've glued them together. So sort of in a bad picture, it'll look like this. And so I want to call this new surface maybe the complex. So the C always means I keep the complex structure. I'm gluing together the points U and V with parameter Q of this surface I started from, and it'll look a little bit like this.
So it's supposed to be an MP2?
At the moment, I'm just talking about surfaces, right? And now I will tell you how I want to connect this to a three-manifold. So at this stage, it's still two-dimensional. So empty doesn't.
Yeah. So, but okay. So if they're two spheres, then it's just another sphere. Is that right? Oh, two disks.
Since they get more slowly.
I was asking if they're two spheres. If I get another sphere. Right, so.
That is true. Are there more questions or comments? Okay, so then in this situation, I can relate conformal blocks on this surface to conformal blocks on that surface by the following operation. So let's see. So I want to write a map between conformal blocks conformal blocks on sigma, which are marked where all other marked points, I collect their markings in a big label R. And then I want to say that I label this by M, some module M, and this by the contragradient M prime. And I want to get a map to conformal blocks of the glued surface, which will be this one, and then these two labels get absorbed, but the other labels stay the same, right? So outside I'm not doing anything, I'm just modifying the surface near the points. And I wanted to take a conformal block here to the sum where I keep all these parameters, I all keep the same, and then in the M and contragradient I sum over a basis, a dual basis pair. And then I have to somehow keep track of the parameter Q, and if I didn't get the conventions wrong, I think it's this one. And so that is something which also appeared in Bin Hui's talk, that there is this doing for conformal blocks, and then they have shown, for example, that for C2 cofinite VOAs that converges, and I'm in the even more conservative setting where I'm sitting on rationals. So that's actually a well-defined map. And so let's give this a name. So let me call this gluing for points UV. I'll drop all these indices soon, and say that's sort of, let's call it star for the induced map on conformal blocks, and it now depends on a choice of M. And so for each M, I get such a map. Right, and you can then convince yourself that it's actually dinatural in M. I will not use that. Okay, so we have an operation which can identify the target here from a surface to the glued surface. Let's see what happens if we want to connect this to three manifolds. So what I want to mean by compatibility with gluing is that I would like the following identity to be satisfied. So now I attach my three manifolds, right? So in this patch, the three manifold will again be the patch times interval. So I get my little ribbon here, which will be labeled by M, and then that's my point U, and then here is my second patch, and here's my little ribbon, again labeled by M, but because the direction is different, this insertion is labeled by M prime, by M contragradient. And so this now describes the map from the unglued surface to the conformal blocks of the unglued surface, but I now apply this gluing map here, GC star for M applied to this, right? So if I do that, now altogether I land in the glued surface, and I want this to be equal to what is the correlator for the following configuration? Again, the inner boundary I don't modify. This is the parameterized boundary here, the inner one. The outer one is the one with the complex structure. So I keep the inner one the same. But on the outer one, I now have glued these two, the complex surface, these two bits of the complex surface together. And so I decide to fill in this tunnel and just connect my M ribbon through this. Right, so now that's again a three manifold with some conformal boundary, and I require that these give the same correlator in the three-dimensional QFT, the tentative one. So these have to agree as functions from what the TFT says to the unglued surface to conformal blocks of the glued surface. Again, with the corresponding labels inserted. Okay. So that's what be how you can express compatibility with gluing.
And if you have M and M prime different, then you don't have any.
So M prime is so M prime is the contragradient module of M. So it's sort of the version of the dual in DOA language. So comments? Okay.
So here it's a sort of trace that we're doing when you glue, no?
Sorry, what?
It's a kind of trace that you're doing in this gluing.
That's a kind of trace. Yeah, you can write it as a partial trace over. I mean, you could think of it as going from M to the completion of M, and then it's a sort of a partial trace. Yeah.
Evaluation.
Okay, more questions or comments? Okay. But now this doesn't look like that anymore. So let's sort of convert this picture into something that looks more like that picture. So I want to take this and rewrite it slightly. So I want to write it again as a gluing, where I cut out the three manifold in a neighborhood of the conformal boundary. Then I get something which is the glued surface for sigma c. Well, here I can then forget the complex structure if I want. I take it times the interval, where then that looks like this. But then I glue to the inner boundary, to the topological boundary, the parametrized one, which is now the gluing without complex structure of the surface. So that parameterizes the inner boundary here by identity. I glue the following. So again, I glue to it the same picture, but I think of it as having cut out the neighborhood of the complex boundary. Well, that's not going to be very visible in my picture because it looks the same. Right, so out here it continues with whatever the surface did look like. So that's a local picture. And now to this, the outer boundary is again parameterized by the glued surface, and the inner boundary is parameterized by sigma. And now on this I can evaluate the TFT, right? So okay, so let me say a number of things. So there are now so now I will want to go in the. Now we finally reach the second part, which is to talk about correlators of two-dimensional conformal field theory. And the way I will do this is I will describe them as elements in state spaces of the topological field theory. Then one can always translate it into actual conformal blocks by evaluating this manifold with a complex boundary. And I will want my conformal field theory correlators to satisfy certain consistency conditions, which are to do with mapping class group action and sewing. And the way I will do this now is by not ever looking at conformal blocks, but instead by just checking how my vectors in the TFT state spaces behave under composition with suitable mapping cylinders and under composition with suitable of these gluing vortices. And I show invariants under those, and then that'll be my definition of a consistent system of correlators. I want to make some comments on how much of this is mass. So how far is one of turning this into a mass statement? So there's a recent paper by Chiara Damiolini and Lucas Woike, who is also here, so we can ask Lucas how much of these details I'm getting correct. So they show that there is indeed such an equivalence of topological and complex modular functors. But I think your description of the topological modular functors may be slightly different from what I'm doing here. So I'm still working on trying to understand how it is different. So it's not entirely clear that the complex modular, so the topological modular functor is maybe or maybe not the one I am building here. But at least there is an instance where one can show such an isomorphism. So that exists. And then in the work of Hui and Zhang, they don't talk about modular functors as far as I could see, but there are proofs of convergence of such sums. And so I feel that maybe if one starts putting these things together, one can maybe show that that exists. Yeah.
Sorry to interrupt you, since we were alluding to Luca's talk. So
Am I? To the paper.
yeah, and the paper and the talk, but we decided to shift the talk to Friday afternoon this week.
Oh, okay. I will miss your talk because I already been on a train, but can maybe watch it online and I'm sitting on the train. But okay, so Lucas will give a talk on Friday right after my, day after my last lecture, and then you can either say that can kind of work or that has no chance of working, or it's something totally different. Okay. Yeah, thank you for pointing that out. I forgot where I was now. Oh, I think I was finished with other questions or comments. Otherwise, I'll go to the second part. CFT and CFT. So let's go back to the basics. So remember that we had our correlator of the easing 4-point correlator on the complex plane. So not on a domain with boundary, and then it was written as sort of some function f plus of z squared plus minus of z value squared. And we wanted to think of f plus as being a conformal block, and this as being a bilinear combination of holomorphic and anti-holomorphic conformal blocks. Now, in the first part, we understood how we can deal with these individual f plus and f minus, namely by thinking about three-dimensional theories which are topological in the interior but holomorphic on the boundary. And now I want to combine sort of holomorphic and anti-holomorphic conformal block to form a well-defined two-dimensional theory. And so I want to set this up, and I want to get to the point where I can give a definition inside topological field theory of what I mean by a consistent system of correlators. So let's see. So what's the setup? So what's my input data? So as long, I mean, we will maybe talk about surfaces boundary tomorrow, but today there are no boundaries, and so if there are no boundaries, there's a priori no reason to make the left, so the holomorphic and anti-holomorphic UAs be the same. So why don't we just pick BW rational UAs? And we think of these as this describing a part of the holomorphic field and this describing a part of the anti-holomorphic fields of this field. Right? And then in the easing example, of course, they'd both be the same, and they'd be very thorough UA, for example, charge a half. Then so these I fix, and to describe a theory with this chiral symmetry, I have to give what are the fields, what are the bulk fields of my theory. So that's a big F, and that's an element in the representations of V tensor W, and there'll be my space of so I have to pick, I have to point at it, right? So whenever I sort of try to give a construction later, it also has to somehow produce F, but for now it's a data. So F is the space of bulk fields. For example, in the easing example, F would be the thorough representation of weight 0, sort of the holomorphic and anti-holomorphic copy, plus the representation of weight 1/16, holomorphic and anti-holomorphic copy, plus the representation of weight a half, holomorphic and anti-holomorphic copy. Right, so that would be how that would look in easing.
Question.
Is F supposed to be an algebra object in red?
Right, and so at this point, no, but then once it satisfies the conditions I'm writing, one can then sort of convert this into saying it's an algebra object in rep V, and then the braiding reversed version of rep W. You box them together.
Commutative.
Right?
Commutative.
And it's also commutative. Sorry?
Lagrangian.
And it's, yeah, let's say more words. Lagrangian. Get another word? No. A trivial twist, go.
So I guess usually people say V tensor V bar. I think usually people say V tensor V bar. Then what does V bar mean?
But you know, what does that even mean, right?
Yeah, I know it's supposed to be like the reversing the braiding structure, but does that actually change the VOA?
Yeah, and because let's just say if we evaluate blocks on this, and so if this lives on the surface and lives on the orientation reverse surface, and that's what we mean by making it.
But when I put the bar, do I actually change the VOA or no? No. Okay.
Because in this specific case of Ising or just in general?
Yes, I say that again.
Are you saying that it doesn't change it just in the specific case of the Ising model, or if I take?
So, so what does it mean to have an anti-holomorphic VOA, right? So you could develop the theory by writing a bar over everything, but then that's the theory you had earlier by not doing that, right? So this is literally a representation in here, right? Now, if I want to talk about this as a commutative algebra, I have to be careful what that I do put the correct braiding on this. But as a representation, I don't think I have to put a bar. And I also wouldn't quite know what I mean by the bar. I usually do this to say anti-holomorphic, and then nobody dares to ask. But
if you want to think of rep V tensor W as a braided tensor category, then you have to be careful.
Then you have to be careful. But I'm just doing.
They're just commuting.
Right. More. Okay. Then see, then I want to, so that's my first piece of data, and the second piece of data I want for my CFT. The coordinates, say I've got one here, so now that's not a three-manifold, it's really just two-dimensional. Then I have some marked points, P1, they again come with local coordinates. And I now, because I want to glue later, I put an extra decoration plus or minus, which determines whether I put F or the contact region of F. And then at each of these points, I want to put a vector either an F, so if it's plus, or maybe if there's a P2, phi 2 minus, then here I want to put maybe a vector phi 2, which lives in the contact region point. So to such a configuration, I want to assign a number, and I want to call this assignment core for correlator, right? And I want these to be normalized so that if all these points are labeled by the vacuum of the VOA, which is part of F, then that's normalized to 1. Okay, so so that's my data. First, put the VOAs, and pick your space of fields, and then pick such an assignment for all surfaces. And I want this not to be an arbitrary map, but I want this to sit in the corresponding space of conformal blocks, right? So what this is telling us is we have to sort of do holomorphic and anti-holomorphic conformal blocks, but the way to think of this is that you take your complex surface and you take its Schottky double, and then it's just conformal blocks on the Schottky double. So the correlator for such a surface lives is an element in the space of conformal blocks for the surface times the orientation reversed. Let me use that for the bit of the double. But here, if I want this part of the surface, I have to use the conformal blocks for V. Here I have to use the conformal blocks for W. And I evaluate that on F to the N. Right, and then I get a multilinear map, and then I have to insert these vectors, and so that is supposed to be the number. So if I don't specify these vectors, I get a, so maybe that's better. So let's not specify the vectors and think of this as an appropriate map out of a number of copies of F into C, and then this should be an element in the space of conformal blocks. So what does this mean? So the conformal blocks on such a disjoint union are just the conformal blocks for this surface, tensor the conformal blocks for that surface, but the conformal blocks here I compute with V, and the conformal blocks there I compute with W. And this, I will abbreviate this as sigma C hat for the Schottky double.
Sorry, I'm a bit confused. When you say I compute with V or W, F is not an object in rep V or in rep W. So
I use the sort of compressed notation of labeling multiple insertions, which is one representation of the product UA. So let me draw a picture and then point. So, okay, so what does it look like as a cartoon? So we have maybe a surface sigma C, then making it into a Schottky double. I get another version which maybe has the opposite orientation, and then the identity is an antiholomorphic involution. And then here I have a point P1 with coordinate phi1, and then in the copy I still have this point with coordinate phi1. With coordinate phi1, which I may have to complex conjugate to make this work. And then I'm saying on these two, I insert the representation F. And what that means is that you can always, because it even makes sense non-semi-simply, but here we are semi-simple, so I can expand it into some U tensor V. Right, and then I say I put U here, I put V here. U is now would be in rep V. This is in rep W. Maybe this U tilde is in rep W. Right, and then I would put U tilde here, and then this I can evaluate with the. I can compute conformal blocks for the VOAB, and here I can compute. I just want to write it like this. Right. There's actually, as an aside, there's a to-do for people who like VOAs. And the to-do is, so here I could make this work by the cheap trick that I've got the surface as a disjoint union. So I am allowed to say conformal blocks for V, conformal blocks for W. And I wanted to encode this by saying I sort of color this bit of my surface by V and that bit of my surface by W. But really what there should be a theory for is that I've got one surface which maybe has sort of a partition into sections, and I'm allowed to label these by different VOAs. Then maybe there's sort of something which one wants to decorate these interfaces by, and so there should be a theory of conformal blocks for such things. And I don't know what that theory is. I know what it is on the TFT side, so I can describe this in the 3D TFT, but I don't know how to describe it in the language of VOAs and conformal blocks. Okay. Okay.
Do you know what data you would put on D?
Hi.
Do you know what data you would put on D, or just not how to make the?
Well, I know what data I'd put in TFT language, right? So in 3D TFT language, that would be probably a domain wall between the Rishtikin-Torayev theory for that category and the Rishtikin-Torayev for that category.
And it would be similar in this story, or it's like you'd need something totally new?
It would be similar what?
In this story, like on the CFT world, it would be very
I
similar.
don't know.
But look, such a domain mode should exist if V1 and V2 are in the same bit class.
Right.
Now we know that then they are related by extensions.
Right.
So if we make the additional assumption that they are related by extensions and that they are local modules of the same in the same category, then we know what to do in the.
Right. Then we would know what to do, right? So I agree. So you can always sort of. So that's actually a question yeah, that's something we can say separately, but we can always try to find like a common rational sub-view A and describe it from that perspective. But it would be nice to not have to do that, right? So that there should be an intrinsic description which reproduces the one where you go to a common sub-view A.
Yes.
Yeah, but then when you don't want to use it, then what is the condition you put on those V's? It's very hard to say without.
I agree with what you're saying. I think it would be nice to have an intrinsic way of how you would characterize these without. I don't know. I tried anyway. So I agree. One can do this. Go to a common sub-view A. But there should be some nice theory for situations like this, where indeed we want these to be sort of topological, that there are canonical isos between this block space and the one where you deform this boundary a little bit. But I think that's not done. I've given you. I've given you data. So now I should also give you conditions. And the first condition is that this assignment should be well defined in the sense that it depends on the argument. So let me just call it well defined. Right, and from what I mean by this is that it only depends on the geometry and labels up to ISO. So up to conformal isomorphism, which is compatible with the local coordinates and insertion points and so on. And so what this will translate into is that if you take a complex structure and you walk a closed path in the moduli space, well, then you have to come back to the same answer. So you can also think of this as being monotony free. For single value. Okay, then it has to be compatible with gluing. Or with sewing, or sewing over there. Let's call it sewing too. So, all right, by the operation we just described, we can sew two marked points with their local coordinates together to get a sewed surface. And so I demand, okay, so let me introduce some notation. So we did have the sewing map. Is that still there somewhere? No. So we have our two patches of surface. And then we have the points U and V. And so now we mark one with plus, so it's decorated by F, and one with minus, so it's decorated by F dual. And then we can glue these 2 points together. So there we had this, so now, however, because we are working with conformal blocks in the double, we have to glue these 2 pieces together. So we start with conformal blocks for the surface C. Again, here decorated by V, W. And then we want to map this to where we glue in this copy the points U and V together, and in that copy also the points U and V together. Right, and so if I write this as this we wrote as the Schottky double, then here I should say I'm mapping this to the conformal blocks of the glued surface for sigma, and then I take the double of the glued surface. Okay, and again, so the points, so here we can mark points f to the tensor n, or maybe plus minus depending on how these points are decorated. And then we have these two extra copies, F and F prime. And then here, we just get this F plus minus to the tensor. And so that was our throwing operation. So let's give that a name. So let me call it the gluing, where I glue the 2 points here together and the 2 points here together. I call it the double of the gluing map. And so that's the map which maps this set of conformal blocks to that. Conformal blocks. It's not an ISO, right? Just a map. Also, with my M's previously, it wasn't an ISO if I pick an individual M. And then I demand that gluing transports a correlator here to a correlator on the glued surface. So I demand that if I take this gluing operation and I apply it to the correlator for the surface sigma, then this has to be the same as the correlator for the glued surface. Yeah. And maybe I should normalize this, but let me not write it down. Yeah.
So just think about the logarithmic setting. Obviously, there's like a small problem with this two sides. I can't quite separate things, but is that an actual problem in the logarithmic setting, or is that?
What's the problem?
When you think about the two surfaces living in different, up there. So I take this double. I think of one side is labeled by one VOA. I think of the other side is labeled by the other VOA. Obviously, there's a small problem with that in logarithmic setting, but is that an actual problem?
What's a small problem?
That I can't separate the coend, for example, into
but I don't have to use a coend.
Or whatever, some algebra object.
At no point am I saying, so at no point do I actually want to know that sometimes this map is an ISO. I don't care. I just want there to be a map from this space of conformal blocks to this space of conformal blocks by gluing a specific label at the punch.
I'm just talking about the setup. Like if I wanted to.
I agree that so you have to be careful what you mean by this, right? Because this F in the logarithmic setting will not be writable as a direct sum U tensor V.
Yeah.
And then you have to go and say, well, left exact and take some quotient and so on.
But is it an actual problem that should I think of that as a problem? No, it's not a problem. Okay.
But I should also say that this theory where you use two different UAs, again, it's not developed, right? So it's definitely not a problem if these are the same, because that's literally the setting of in Hui and Zhang. This probably also works, but not fun. Okay. Not so great. So I want to at least, I want to now translate these two conditions into TFT. And then that would maybe be a good place to stop. Oh, I didn't call this section something. So what I did up there should have been section 2.1, which is called closed CFT, the statement of the problem which I want to solve. Maybe pick the data subject to these conditions. And now there's a section 2.2 where I translate this into TFT. And so what's the setting in TFT? So what's my data? C and D is modular fusion categories. And then I think of this as representations of V, right? So to relate it to what we had before, this is rep V and this is rep W. Then I have to find an object in C box. And now later I will want to operate with this as a braided category. So now I'll be more careful and say I want to use the braiding reversed version of D. Pick an object in here. So that's my piece of data 1, the fields, and then there's this piece of data 2, which is the TFT presentation of these correlators. which, right, according to this picture, should be TFT states for this sigma being the double of the surface I want the correlator on. So I want to have some collection of elements gamma, which depend on a surface with marked points and these plus minus label as before. And that should be an element in the TFT state space where I have some of these surfaces. So where I take the surface and the orientation reverse version of the surface, and I take the disjoint union. Again, I should put here a label C, which means I take the surface sigma and evaluate the TFT for C on that one. And I evaluate the TFT on D for that one and tensor that together. I should also label them. And so I use again this trick where I use sort of label pairs of objects by representation here. So again, it's translated by F plus or minus, depending if I do F or F dual to the tensor n. And so that's sort of what I'm doing here is I'm secretly already using an extension of this Versticken to IF TFT, where I am allowed to work on stratified manifolds. Where different components may be decorated by different three-dimensional regions, may be decorated by different modular categories and contain ribbon graphs in that respective modular category. I'll say more about this later, but let's just do it like this for now. Okay, so I've got this element, and so then I want to say what are the conditions. They are one, mapping class group invariance, and two, compatibility with gluing. So mapping class group invariance. So let's say I've got a diffeomorphism F, which goes from some surface sigma to another surface compatible with the marked points and the plus minuses. Then out of this, I can get a Bordism, which goes between the orientation doubles. So I do the orientation double, and then I also take the double of the mapping cylinder over F. So this gives me a Bordism from here to here, the mapping cylinder, and so therefore I also get a Bordism between the double surfaces. So that's what this one is. Double surface. So one copy of the mapping cylinder, the orientation reverse version of it for the second copy of the surface. And my condition is that a gamma of the target here has to be equal to the TFT applied to this mapping cylinder acting on gamma C. And so these elements are compatible with the action of the mapping class group. And then there's gluing. And what gluing
theories to be anomaly free?
I am not requiring the chiral series to be anomaly free, but for the combination, I think I would want that. Yeah.
So the linear product would be anomaly free.
So therefore this. So later I would want. So it will come out of the way I will construct these later, that that this product is anomaly free. Okay, so what's the TFT presentation of gluing? I've got two surfaces which are maybe here two patches of it with my 2 points U and V, and then we had this Bordism where so we had the glued surface G sigma. Which looked like, I should have drawn this on top maybe, which looked like this, right? And we had a way to turn this into a Bordism by passing a ribbon through here and calling this X. And so this this bordism I want to call, I think I wanted to call it MUV, the gluing bordism, where I label the ribbon which passes through here by X. Okay. And then I can do a double of this. Again, I remember the points, and I have to be a little bit careful with my labels. So I get two labels now because I'm doing two copies, and it goes from the double, where in one copy of the surface, maybe this one, the point is labeled by X, and in the other one it's labeled by Y. And that goes to the glued copy, to the double of the glued surface. Then I can extend this linearly, and then it makes sense to ask that if I apply the TFT to the double of the gluing here, and I label my my pair of points just by linear extension by this object F, and I apply this to gamma of sigma, and that has to be gamma of the glued surface of sigma. Okay, and so if I can say one more sentence, I'll write one more definition, maybe I write here. So that's our starting point for next time. Then we will try and write solutions. So a consistent system of correlators is for C and D is this F and gamma as above, satisfying these two conditions, satisfying one and two. Okay. And so that's my translation of writing single-valued correlation functions in CFT consistent with sewing and as a TFT problem. And then what we will do tomorrow is to write solutions to this TFT problem, also with the help of 3D. Okay.
Questions?
So in this maybe anomaly-free setting, is this identification between the topological state spaces and conformal blocks like canonical or something? I guess there's some. I think I'm reading implicitly that you're going to say that the topological state spaces are identified with conformal blocks.
I want to always use this method, right? So I assume somebody constructed this for me.
Yeah.
And then I can plug this into the conformal blocks for C, for the B, for the holomorphic thing, and for W, for the anti-holomorphic thing, and then that should.
But I guess you're saying this is real. This exists in the.
I assume so. If somebody constructs that for me,
yeah,
then this description of correlators and TFT, will, if I pass it through this correspondence, give me actual conformal field theory correlators which depend on the complex structure. And
yeah, but my question is, are you going to tell me that that actually exists in the rational case?
No, I am telling you I believe it to exist, and I am telling you that sort of there are some works which go in that direction, like what Chiara Damilini and Lucas Voike did. But I don't think it's literally yet that. I think maybe you can tell me better. You cannot.
Not spontaneously. I mean, we have a statement in terms of modular functions, where we have the statement that there's the VUA modular function, and that this is really a modular function in the sense of, say, Bakalov and Kirillov. But yes, I'm not entirely sure whether this is exactly what you said.
So I feel that one can make that into a theorem, but I'm just saying it's not a theorem.
So in the rational case, there's still a little bit maybe missing that we would like to understand.
From that point of view, yes. From Lucas's point of view, no.
Okay, Lucas is going to solve it. Is that what you said?
Yeah, setting in which this can be made.
Okay.
So at the general level, how predict? I mean, like if you want, can you like this theory can predict? Can like compute? I suppose that you can compute the minimal model correlation function. I mean, like to give a structural constant and the decomposition.
Right.
And can you go further, like for non-compact theories, like?
Well, that,
Like,
again,
can you find the Liouville theorem?
so that's a to do for that's maybe a to do for the Liouville theory working people is if there's a probabilistic description of these correlators for you give a sort of a complex surface and with some insertion points and then it hands you back a number, right? So it's a probabilistic setting. So maybe there's a probabilistic setting for these three-dimensional theories as well, which hence you need conformal block, right? So these depend holomorphically now on these insertion points. Maybe that has a probabilistic setting, but then that would be well defined. And so then you could pass, then that would entail that you have defined a 3D TFT for Liouville theory, which in itself is a non-trivial thing because all infinite dimensional state spaces. So I don't think it could, so as a meta idea that should work, but then there are sort of, to make that precise, I see a number of hurdles which I don't see how to overcome.
You should probably partially define only.
And that's fine here, right? Because you never have a situation where there's no, so there's either a conformal boundary or a T, so you wouldn't want to talk maybe about closed manifolds anyway in that setting.
This is not a question to you, but for the whole audience. Jörg Teschner was mentioning something called Liouville TQFT, and he referred to papers by Eberhard and company.
I have not looked.
Does anybody have an idea here in the audience to what extent Liouville TQFT is a TQFT in the sense we would think
As a
it is?
function from a catch or something.
Yeah, and we are flexible about the coordinates and everything. So that would help for your program, yeah. And I think it's an urgent thing.
No, it would help for our problem.
Yeah, it's not a problem.
Yeah.
In this example of the Liouville theory, is there an expectation of what the modular category would be? Of course, it wouldn't be modular because the objects would not be finite and so on and so on. But is there any kind of expectation and conjecture?
Well, I can say some words, but they are not, I don't think they have meaning in math. So you would take, you take unitary representations of the Virasoro VOA at some central charge greater than 25. So that thing is a difficult category because if you tensor two objects together, you get a continuum of objects. And so really you want to work in some sort of C star setting of tensor categories to make that precise. And I think that does not exist at that point in time. The setting exists, right? So that's maybe it can be fit into the setting that you're working on, but I don't think the actual Virasoro representation you have written down yet.
I think the part about the block, everything you wrote about the block, now it's fine. I mean, it's going and so on.
Okay. Can you make that probabilistic?
At least I don't really understand.
Okay, I will say it again.
Maybe if you explain me more.
Okay, so we can, thanks again, Ingo.